I'd like to welcome everybody today. My name is Jeff Benty. I'm your moderator for today's session. I'd like to thank everyone for joining us. Our topic of discussion today will be can proprietary BMPs help LID practices on your project? If anybody's having any technical problems or anything, you can email me or give me a call directly. I'll put my number up on the screen in a moment here. But before we get started, I'd like to talk a little bit about our speaker. John Mall received his education from Florida State as a geologist. Over the years, John has worked in the landfill industry and the mining industry and owned his own civil engineering firm. John, in conjunction with Clark Hughes, are the inventors and owners of the Crystal Stream technology. John currently operates as CEO and oversees and directs all research and development projects, and has played a key role in the Stormwater Equipment Manufacturers Association. With that, I'd like to please have everybody join me in welcoming John. John, the floor is yours.
Thank you, Jeff. Folks, I'm glad you're here today. This is a very important subject, and I want to explore LID as completely as I can and kind of let you know some of the issues that are out there. I was watching the NPDES, the non-point source list server, the EPA's list server this week. They were discussing infiltration practices, and some of the folks publicly and privately were reporting high failure rates of infiltration practices and some other things. And so I think this is kind of an appropriate subject for us to talk about how sometimes proprietary BMPs and manufactured products can help enhance low-impact development. We know the NPDES Phase 2 kind of phased up, summed up water quality with their 6 minimum control measures, which is public education, public outreach and involvement, eliminating illicit discharges, construction runoff control, construction phase, post-construction phase runoff control, and water quality being included in that, obviously, and then pollution prevention and good housekeeping. The low-impact development means a lot of things to a lot of different people. This definition is off of the low-impact development site, and it says that low-impact development is a comprehensive land planning and engineering design approach with a goal of maintaining and enhancing the pre-development hydrologic regime of urban and developing watersheds. This is to be accomplished while meeting the water quality goals dictated by NPDES rules and regulations. And the two subjects are actually complementary, but it's important to understand, and for those of you who've been here before, I'm going to try to use the highlighter pointer here. This thing has a way of making my menu disappear, so but I want to understand want you to understand maintaining and enhancing the pre-development hydraulic regime, and this is not as simple as doing detention. So it's something we need to think about. So so the main goals of LID are to match the pre-development conditions for quantity and quality. And for those of you who aren't necessarily familiar with these terms, quantity is the volume, the total volume of water that runs off a site. And quality also can mean the rate of runoff, and we'll kind of break these down a little bit. And quality, water quality, of course, are the contents of the water, which is usually degraded when we develop a site. So you want to have the volume of runoff, which would be maybe 20,000 cubic feet detention in a pond. You think of that as the volume that you're holding, but really the volume of runoff changes as sites develop, and that's why we have ponds. But the ponds are there to control the rate of runoff. So what we want to do is prevent changes in the concentration of pollutants for water quality. But every time we increase impervious surface, that means there will be more water runoff. I'm going to kind of show you how that's figured. And it also usually means a higher rate of runoff, that the water will run off faster. So changing the type of material of surface, of course, will change the type of material that washes off. Most hydraulic hydrologists and engineers believe that about 95% of the water that falls on an impervious surface will run off. Just to take a little short rabbit trail here, they're talking about the annual runoff rate. There's a thing called initial abstraction when we're using a TR55 or SCS method of calculating runoff. And essentially it means that there's water that evaporates when it hits a warm surface. There's water that's caught on the leaves of trees. Every kid has probably stood under a tree when it's not lightning. During a storm to kind of stay dry. So there's the 95% is not every storm every time. And of course, when a surface is saturated and it's a heavy runoff, the runoff is probably closer to 98% or maybe even 100% or close to 100%. So, but in developed landscape areas, about half the water runs off. This would be a constructed lawn where the surface has been prepared and sod was put down. It might be less than 50% for an area that's been planted with trees, might be more on a lawn that was well compacted underneath. But an undisturbed forest land, only about 20% runs off. So we like to use things called C factors and percentage of runoff, but essentially when an inch of rain falls in the forest, annually about 2/10 of an inch runs off, about 1/5. And it could be as low as 1/10. This is part of the, I would call it art or magic of doing hydrology. Different engineers have different opinions, and they talk about how long the storm takes to run off. But that's why you'll see a variety, and why hydrology is an inexact science. But when forested land becomes a pavement or a rooftop, almost all of it runs off. So we can generalize and say about 5 times as much water runs off annually when we develop an impervious surface. And we can also say if that 50% is close to right, some people use 40, some use 60, but even the landscaped areas, man-made landscape, produces maybe 2.5 times the runoff as forested land or undeveloped land. And of course, it depends on the type of land. There's prairie and there's forest, but we've got to use some generalizations here to get an idea. But the point I'm trying to make is that there's going to be more water runoff no matter what. And secondly, the water moves more quickly across paved surfaces or perhaps in pipes. And so not only does more water run off, it runs off more quickly. So there's kind of a dual thing at work here. This chart's been passed around among a lot of people. I believe the Center for Watershed Protection originally developed it. And there's some challenges to these numbers. In fact, this chart kind of favors infiltration, and there's been some studies showing, well, maybe it doesn't occur at quite that rate. But that's not the important thing here. The important thing is that when you have natural ground cover, as much as 40% of the annual rainfall is lost to evaporation and transpiration, where you have this water that will be absorbed for a moment and then released back to the atmosphere. And part of it, 10% runs off. I say 20, but 10 is a good number. 25% goes to shallow infiltration. And this would be like a perched water table, but it's not down in the saturated zone as a hydrologist might think about it. And then 25% to deep infiltration. And as the site's developed, a site is developed with impervious, these numbers begin to change. And at the very end, some believe as much as 30% is still lost to evapotranspiration for a fully impervious site. And 55% of it runs off, and there's very little shallow infiltration and less deep infiltration. So there's a change in characteristics of obviously the volume of water that runs off of a site. Now, through the 70s and 80s and up through even today, we gathered this extra water and we detained it. That's where the word detention pond comes from. Sometimes you'll see detention and retention, and actually they're two different things. A pond that retains the water on site. Retention, a pond that detains, slows the water down. This is an example of a pond, and essentially there's what we call a V-notch weir. A weir is an element that controls the flow of water. It could be a broad wall. It can be a hole or an orifice. It could be a standpipe. There's all kinds of things that control flow. But this particular V-notch weir is done so that as the water gets deeper and there's more volume being stored, that would indicate there's more flow that has come into the pond. The V gets wider, and so more water can flow out. This is a way of matching, what we would call matching the rate of flow. Small storms have small flow, and a V-notch weir with its small area on the bottom would let low flow off. So you kind of match the pre-development rate of flow. Rate of flow means cubic feet per second, not cubic feet, which would be the volume, or cubic yards or gallons, or however you want to look at it. But the rate of flow can be matched this way. In bigger storms, the pond gets deeper, and the outlet control device allows more water to flow out. There's quite a bit of attention paid on sites to the outlet control structure on a pond, the detention pond, to keep the same rate. And why would you keep the same rate? You'd keep the same rate because there might be a culvert downstream, a 24-inch pipe under a street, and you don't want to overload that pipe by having a greater rate of flow. There may be a swale that goes to it. You could have a neighbor that's used to a certain flow coming off of his property. So the requirement to match the rate of flow has been around for a while. and matching the rate control is actually pretty easy because there's vertical slots, there's a thing called a Cipraletti weir, there's circular weirs, there's a million ways, not a million, but there's a lot of ways to use outlet control. And then if you match the rate of flow off the property to the pre-development rate of flow, which the engineer determines using the type of surface and the amount of tree cover and other things, hopefully he gets the rate of flow the same, leaving the property. But because the rate's slower, volume builds up, and that's why we have pond volume. So we have to weigh, if we're going to control volume as well as rate of flow, we've got to find a way to use water on site. So there's another problem, though, with simply matching the rate of flow. You do catch some gross pollutants and some sediments, but even though the rate of flow, let's just say 5 cubic feet per second, matches the pre-development flow, because this pond is storing water and more water is running off, maybe 5 times as much, that rate of flow will last 5 times longer. As that rate of flow, that extra volume of flow reaches the stream, it has an impact on the stream. And we'll talk about that a little bit more, but essentially you're putting more water in the stream. You may be putting in there more slowly. There's some pretty nice techniques that talk about where you are in a watershed and how long you should hold your water, and whether you should release it over a longer period of time than just strictly trying to match the rate of flow. Also, the amount of time water spends in a pond, if you simply match the rate of flow, is a relatively short period. Let's say a storm lasted an hour, and because it takes 20 minutes for the water to get from the top of the basin to the bottom, the entire flow lasts an hour and 20 minutes. If you've got 5 times the water released at that same rate, you might end up with 5 times the amount of time for that storm to release, say 6 hours instead of 5 hours and 20 minutes or 7 hours. The footprint of the pond is small in comparison to the impervious areas on the site. So where there is a possibility of infiltration in this pond, and since the water may sit there 5 or 6 hours, it has a good opportunity to have some infiltration. But the pond being deep and as small as possible, typically developers and engineers want to make these ponds as small as possible. So infiltration of the groundwater table is limited, and of course water is not going to infiltrate through the impervious surfaces, the ones that can't be penetrated by water. When you get to a large storm, even if this pond has been set so it releases over, say, 48 hours, you reduce the rate of flow. When the big storms come, usually you will hold maybe a water quality storm, which might be 1 inch first flush, and you'll hold it for 48 hours. But if you get a 4-inch storm, those last 3 inches go out over the weir. And so the larger storms, when they come into a pond that has a low energy, it can stir up mud and trash and debris, and so you can lose a lot of material. So a detention pond, certainly one that's not set up for water quality, can't do anything about the volume of water, 5 times as much. It might not do very much for water quality. In fact, it might even degrade water quality depending on how the pond is built and what the energy gradient is across the weir. So jurisdictions are going to require detention, and it's a good practice. It's the right thing to do. You wanted to do it to protect nearby properties and pipes and swales, but it cannot really address water quality problems per se. There are credits given because we watch these ponds silt out and we see them fill with hydrocarbons sometime and trash and debris, so it's having some effect. But as a larger percentage of properties developed across a watershed, more and more water reaches the stream. And I say sooner or later. Normal detention, maybe it's 5 times as long as it might have taken to reach the stream before because it was detained. Maybe it's 2 days, but still there will be more volume of water get to the stream. Also, that water tends to hit the stream faster. Pre-development flows were smaller, but they took longer. So with pre-development, more of that water is infiltrated into the ground, and we call this a base flow to the stream. This is water that goes into the saturated zone, into the water table, and migrates horizontally to the stream. So you get some stream flows even though it hasn't rained in 2 or 3 days. You'll get some flow support into the stream. So when you get the higher volume of flow into a stream immediately after a storm and almost no infiltration, you get no base flow for the stream. So when you get that higher flow for short periods of time, relatively short periods of time relative to what happens when the water infiltrates and goes through the water table, days and days and days to get to the stream channel has to widen, and it has to accommodate these higher flows. And the whole shape or morphology of the stream has changed. So rate of flow is not a problem. In fact, many BMPs have been shown, tested. Now, some of these are manufactured. There are others that have been shown to be very effective. I say manufactured. All of them are manufactured. I use manufactured to mean proprietary manufactured devices. But many have been shown to be able to effectively remove the pollutants that we have that are concerning to us in water quality. But almost none of them address the runoff volume problem, even underground storage chambers and pipes. Volume is the challenge. So manufactured solutions can help with other problems, but can they help with this volume problem also? It's a physical problem. There's too much water and only a few ways to use it on a site. So if you're going to reuse the water on site, there are some fairly common ways, but you have to be aggressive and effective in your pretreatment. You can't have trash and debris and all sorts of vegetative material and sticks and gravel going into most of these uses for reuse on the site. And you have to accommodate a way to store that water. So infiltration into the ground, uptake by vegetation, which will then allow the water for them to respire, for the water to come out as water vapor out of the plant, and evaporation are best addressed by land-based BMPs, not manufactured proprietary BMPs. Reuse for gray water, that would be washdowns, cleaning, flushing, and irrigation. These options can help save critical potable water supplies. In other words, all the water you're using for irrigation, flushing toilets, or cleaning or washdown, which goes into the sanitary sewer system, saves buying water that is treated for drinking water purposes. So here's the challenges. Stormwater is dirty. Rainfall is chaotic. I'm showing a picture of a storm here that's getting some awesome rainfall on the right side and not so much on the left side. And this is the way storms work. It's difficult, and it's difficult to control the source of trash and debris when a site's being used by the public. It's also hard to control the flow, to understand what the flow is going to be a block apart, two properties a block apart, much less a state apart. And owners are uninformed. Owners who don't know what a BMP is, and I could give you many stories about having seen these in the field. They don't know what it is, they don't know what it's for, and they certainly don't know what to do with it. This includes individual property owners and homeowners associations or merchants associations. So going over the stormwater is dirty piece. Whether you're infiltrating, irrigating, or reusing water, pretty much have the same similar needs. You want the water coming to them to be free of excessive sediments and gross pollutants. That's a challenge, but gross pollutants and sediments have proven to be relatively easy to control. This can be done with a manufactured treatment device. There are public domain solutions that can also accomplish this. Sometimes these manufactured devices only have a manhole or two in a parking lot on the site. They're under use. They're under an area that has another use. That would be maybe parking or landscape. So it's not using up area like a pond might, where you certainly can't park in a pond. Might not want a landscape in a pond, depending on whether you're trying to plant some hydrophilic plants that'll help out your pond. But whether it's a manufactured device or a public domain system, if it's well designed, the material's easy. The material capture is pretty easy to remove and dispose of it. So there are some things that are extremely hard to clean, like bioretention and constructive wetlands, rain gardens and some other things might not be so simple if they're impacted with oil and hydrocarbons and trash and other things. Not quite as simple to clean a wet pond, for example, as it would be an underground vault. So we know the rainfall is chaotic. Infiltration is slow. So when it rains at a rapid rate, rains hard, infiltration can't keep up with it necessarily. Bioretention has usually has limited storage before it goes on overflow. And then reuse systems, like a cistern, they have to hold enough water to provide for irrigation and other uses. It's ironic, a cistern, which is used to irrigate landscape, is nice, but when it gets full from a storm, you just had a storm, and you don't necessarily need the water that day. And when you have a prolonged drought, the cistern is not likely to be full. So you have to be careful how you size a cistern to actually have water when you need it. And there's a lot of techniques where folks are using potable water to supplement the cistern. And if the cistern's full and you get a storm, you're going to, quote, waste that water. So large storms can be problematic for all of these things. So when these things don't work well because they can't take a large flow, you generally have to go to a detention or some sort of storage where you may have a reuse at another time. Small storms, of course, may not give you enough. And irrigation is a nice concept, obviously. And I did another seminar here where we talked about where the National Turf Association said, hey, if you've got a really great turf lawn, here's how much water you could use. And I was surprised that at about 40% impervious, even if you had perfect turf on the rest of your property, you just could never use all the water for infiltration. You had to come up with another method. So we're looking at infiltration fields such as porous paving. This can have a problem if it's in a low point, but if it's at a high point where you're spraying irrigation water onto it, water that's not needed to irrigate your turf for that particular time, and this goes into a sand filter underneath the porous paving. There's a lot of things you can do to, quote, waste that water or delay that water and put it into a slow draining system, such as might be under paving. So there's other things you can do with your water to use it as opposed to directly use it for irrigation. So if you look at the stormwater manuals, I could refer to Georgia or Tennessee, Maryland, Virginia. In most areas, they pick a 1-inch first flush. I think Nashville's 1.14 or 1.2 in Georgia. There's a couple of different things, but what they're looking for is they want to take all of the 1-inch storms and account for 80 to 90% of the rain that falls every year. Now, I'm using 50 years of rainfall data from Atlanta, Georgia, Atlanta Hartsfield Airport. In that particular database, only 65% of the storms are 1 inch or smaller, okay? When I say 65%, I'm talking about 65% of the annual volume is contained in storms that are 1 inch or smaller. And you go, well, so 1 inch won't make the 80. But a volume-based BMP, a pond, for example, it's also going to catch the first inch of all the storms over 1 inch, 1.2 inch, 1.5 inch, 3 inch, 4 inch. When you add those inches for the larger storms, in Georgia, that comes up, I think, to about 87, 88%. But the point I'm making is on a volume-based system. Now, most manufactured devices are flow-through, so you can keep that kind of in the back of your mind. That 1 inch first flush is a pretty good approximation of holding 80 to 90% of your water. Let's use 80 as a worst case. If you remember, forested land only has about 20% runoff. So if you did catch 80% with a 1 inch first flush, you could match on an annual basis the existing volume of runoff. That might not be good in individual storms, but the point I'm trying to make is this, our first flush volume is probably a pretty good starting measuring point for what we want to catch, hold, and reuse to duplicate volumetrically what used to happen on the site before it was developed. So anything that can be caught and retained on site can help meet that goal. There's some simple things. On what I would call tough commercial sites, that would be highly developed hotspots. The rooftop is 30, 40, sometimes even 50% of the impervious surface on the site. The solution of a lot of folks is to take that water and run it across a parking lot. The water is relatively clean coming off of a roof. There's some atmospheric deposition of nitrogen. There's other things, smoke and debris and fly ash and all sorts of things could settle on a roof. But by the way, that also settles on the impervious surfaces like the paving and other things, including landscape. The point I'm trying to make is that water's a bunch cleaner than most of the water that would run off of a parking lot. Probably not full of trash and debris, and probably not full of vegetated trimmings and material, although a tree over a roof could do that. But that water would be the first water to use to fill a cistern for irrigation or for secondary uses like wash down or cleaning. It could replace drinking water, potable water being drinking water, which would save some money on an ongoing basis, certainly, if you're not buying the water. It can allow you to irrigate. You can irrigate at a rate that helps foster infiltration and avoids runoff. I've seen some irrigation systems that are spraying water onto an essentially almost impervious lawn. I saw one yesterday, and the water's running in the street, and I don't know if that irrigation system was fed by a cistern. I certainly hope so. At least it was not doing any extra damage for runoff. But if it was fed by potable water, they're taking drinking water and putting it on the lawn so long and at such a rate that it's running off into the street, actually causing additional runoff. And if you have a rain garden or bioretention, and this is where a lot of residential roof drains are run to rain gardens, and I've seen some articles lately about how they really don't do anything and how residential rain barrels don't do anything. Well, they do something. If nothing else, they make people aware of the fact that they need to contain the volume of runoff coming off their property, and that they can make some use of rainfall. And no matter how small that effect is, it's a measurable effect. And if you had a cistern that you had on overflow, you certainly could direct that the same way you would pump it out on your lawn. You can certainly direct it to a bioretention area or to a in-ground infiltration where you might be able to utilize that water to get the benefits of evapotranspiration and some other things. So there's other places that aren't so simple. I think roofs are pretty simple, really. and they are highly unused. A lot of good engineers today are carefully piping their roof drains so they don't have downspouts, but you know, the first thing they do is find the nearest manhole and commingle it right back in with the stormwater. Yes, there is a cost associated with some additional piping to segregate that water, and yes, there's some cost associated with storing it. But I've seen many systems where they are essentially storing as clean of water as they can coming from their roof. And by taking that 30 or 40% off of the drainage system, not only are they doing good water quality, they're downsizing their pipes, they're downsizing their pond. And so this can be a winning proposition, not a losing proposition. Sometimes all anyone can see is another 100 feet of PVC pipe. But the benefits of not using potable water are long-term, and there can be direct, immediate benefits to downsizing the pipe system on a property. So some of the areas that aren't so simple, this is where we start to look at how manufactured products might be able to help. The water that comes off parking lots can be full of pollutants, and it needs pre-treatment. The things that do really well at storing water and at infiltrating water and using it for bioretention and getting it to plants definitely do not need dissolved metals, hydrocarbons, tons, literally tons. Our research shows close to 6,000 pounds per acre per year washes off these sites of material that we can measure. And this is material when measured and done, particle sizes done on this. I'm talking it's 55% sand, it's about 7% clay, and about 38% silt on average. And so when all of that washes into an infiltration system or a bioretention system, of course the sand occupies space and is pretty visible. The silt does the same, but the smaller silt and the clay-sized particles tend to get in and clog infiltration systems and cause trouble. Not only that type of trouble, but visual trouble. The water looks cloudy. It looks turbid. It doesn't allow UV penetration. So manufactured solutions are good at this, and you don't want to get a manufactured solution and say, hey, I'm going to necessarily control my volume with it, but this is where manufactured solutions shine. Most of them have been shown by lab testing or field testing to remove 80 to 90% of the solids. If that's true, and solids are what impact the life of a pond or an infiltration area, you just extended the life of that system and the effectiveness of that system by a factor of 5 to 10. Most of them are easy to clean. When I say easy to clean, you look at that bottom picture. I use it a lot. That is not easy to clean. It's not fun to clean a vault-based system. We've got a vacuum trailer shown in the top picture there, but it is a ton easier than trying to clean a wet system. And even a pond like this may have a standing flow so that you have to make elaborate preparations to get it dry, to be able to get in, to be able to get the sediment out of it. So it's a little tougher. The maintenance and cleaning for these land-based systems is also cut. The life is extended, but the maintenance and cleaning is also cut by a factor of 5 to 10. If you look at the statistics that were published in the latest studies that say $600 to $800, some say as high as $1,200 per acre for manufactured systems to be maintained, those same studies are showing now $4,000 to $5,000 per acre per year cost to clean land-based systems. So if you're going to cut that maintenance by 80 or 90%, that's a big number. In fact, the number starts to line up with the manufactured system maintenance, and the two together are a much smaller number. So if you're looking at LID and you want to do LID, it's a great thing, because remember, it does the things that a manufactured system cannot possibly do. But the manufactured system can make it work better, can make it less cost to maintain, and suddenly it becomes doable. We don't need somebody publishing 25 to 40% failure of infiltration systems. That might be true, but we need to have a 90% or a 95% success ratio for these infiltration systems that recharge the water table and do again what a manufactured system can't do. Now, owners also are uninformed, and I could take out owners and put contractors are uninformed. I've seen contractors who were told not even to walk on the surface where there's going to be an infiltration system installed. Maybe, let's say, chambers and gravel over scarified soil that are compacted with a sheep's foot because they're worried about bearing after the system is in, even though the system's been tested and even though the manufacturer's instructions are clear. So contractors can have their problems, but owners typically don't know the function of BMPs in their site. And we have confirmed this time after time after time. When the plans are being done, there's a checklist that's required and a maintenance schedule that's required. And what I hear out of the jurisdictions often is, boy, we don't have this. We don't have the staff to go inspect these things. The owners don't know they have these things. Someone's going to make sure their air conditioning filters get changed and the filter maybe in their water cooler inside. They get a little manual with these things when they get their building. They probably hire someone to do that for them. But as far as BMPs, it's a couple of manholes on top of the ground or a pond back there that they don't know that they have duties and responsibilities outlined. Some do, and some do take care of it, but it's certainly not the rule. It's the exception for the people that really take care of that. Every BMP, proprietary or otherwise, should have a manual showing proper care and maintenance. I believe maintenance procedures and the cost should be disclosed at the time of issuance of a permit. I've seen areas with deed restrictions and other things that let people know and make sure people understand when they buy a property what they are buying with it. And designers should disclose maintenance procedures and costs before a BMP is included on the site. You can believe that a part of our sales effort here at Crystal Stream is to explain to people, yeah, they can do something that might not be effective and it might be able to be approved and it might be cheap, but if they really want a good long-term maintenance strategy, they need to pay attention to what's going to happen to that BMP. You know, it's not necessarily to have an army of inspectors out there. Owners can self-verify it at the proper inspection or maintenance interval. There are cities where we do maintenance, where we take a picture of the front of the building and the address. We take a picture of the BMP. We take pictures as we clean it. We provide a three-party manifest showing we were there, that we hauled it, that we disposed of it. Those jurisdictions require this to be submitted either yearly or every 6 months from the BMP. And they only then have to deal with the exceptions. And yes, it takes a little bit to get a program like that started. But over time, it becomes like a check-off list for the restrooms at a gas station. If this was checked in July, it was checked in January, it was checked in July, it was checked in January, it was cleaned in July. And these sort of reports and sort of things are easy to manage. I mean, there's hardly any software out there that can't do a tickler system to remind you when the next maintenance or next letter or next proof of maintenance is required. And remember, the EPA did not just throw out those minimum control measures in any willy-nilly order. The number one minimum control measure is public education. If you don't have the public aware, and that means the people that own these BMPs, the inspectors can be aware, and the regulators can be aware, and the engineer can be aware, and everybody can have these nice sets of blueprints that are rolled up in a closet somewhere, and nobody knows what's really happening in water quality. So public education is something that should be left out of this. This is a picture of a couple of things. We study when we clean a BMP, this is for a particular store. I think it's a drugstore. It shows what we found. It shows that we cleaned it, we hauled it. We charged them $250, I think, here for disposal. No, 250 gallons on this particular one. But it's a way to verify that we did show up and we did do the work. And if an inspector comes to that store and goes, hey, are you taking care of your BMP, the fellow can pull out his records. And we also send it, of course, to the state and to the jurisdiction, and we try to get everybody covered on this, keep it ourselves so that everybody knows we did it right. So here's just a little recap of water quantity with water quality. You've got to address runoff volume first. It's amazing to me today that a lot of engineers get to the end of a set of plans and the end of a pipe and go, well, let's stick a BMP on it that ABC jurisdiction will approve. First thing on runoff volume is retain and reuse if you can. not only can you get some lead points, and not only can you, it's coming, the reuse of water on site is coming as a requirement, but you need to get in the habit of looking at that first. Limit the exposure of clean water to hard surfaces. It's not necessary to run your water across hard surfaces. Limit and protect source areas and disconnect impervious. So these are things you all know that if you've been around water quality for long. Certainly pre-treat ahead of ponds, infiltration, and bioretention. The worst case scenario is when you have to hook a crystal stream unit on the end of a pipe that has no treatment upstream, and you're going to try to get all the pollutants out of moving water. And it's a challenge. And I say worst case, that means you didn't plan. We love to sell the units and you want to get your permit, but if you use a little bit of intelligence up front, including addressing that runoff, you could buy a smaller crystal stream. Not that we're trying to downsize our units, but I'm trying to point out to you, design is the time to address this and address the volume first. There will be places, a scrape and rebuild on a steakhouse, that you just can't do anything much. Inverts can limit you. The type of soil you have can limit you. The amount of landscape you have can limit you. But you need to think that way. You need to think of addressing runoff volume first. The reuse saves money. Of course, it helps the environment. It saves land, smaller pond, smaller pipes, smaller BMPs. Maintenance is simplified, and you get your costs identified up front. And the removal of material provides a tangible result. We just gave an award to a city in Tennessee. We welcomed them into the 100-ton club, which means we have taken 200,000 pounds of material, which is a load, literally, out of their stormwater that was going to go in their trout stream. And any owner, we can do this for anybody that's had maintenance, whether it's our product or anyone else's, we can give them a certificate showing how much material we disposed of, and it is a tangible result. So to try to avoid the worst case, every gram of pollutants that doesn't enter a stream or a pond or a downstream BMP makes the job easier. So control your sources. This might be an awning over a truck dock, as simple as that. All the water retained on site reduces the rate of flow and the duration of flow. If you think about that, it's important. Not only do you make your pond smaller, you're helping your stream. And in the removal process, slower is easier. And so once again, you reduce the flow and your BMPs are going to work better. So don't ignore the design factors when you're sitting down and beginning work on the site. That can make your design process easier, but there are tremendous savings of scale that are long-term savings here. I don't want to make light or de-emphasize the role of the owner, but sometimes as a designer or as an engineer or an architect, you kind of need to lead the owner a little bit and say, hey, we're going to come with this plan. This plan is going to cost you $30,000 more, but it's going to save you $500 a month, and this is a 5-year payback or whatever the number, that's 60 months. I think I got that pretty close to right. And then the savings go on, and not only that, you'll have more land because your footprint is smaller, and you'll have less maintenance because your pond will last longer. So there are a lot of BMPs that can help you. The worst case, when you start with construction site runoff, I'll just mention the fact that that material, which runs off about, I'm in the crowd that says it's probably 30 times as fast as a developed site for physical solids running off the site. And I've got some calculations on that, and they vary. But first things out, don't ignore the control of sediments during the construction process, because all of those sediments, especially anything that gets down into an infiltration area, can have a huge impact, So you want to stabilize erosion control, which means don't let the soil get loose, as opposed to sedimentation control, which means let's try to control it. Now that it's gotten loose, let's try to stop it with a siltation pond. There's some things you can do to keep pollutants out. You know, drum pallets, cisterns. I've mentioned the overhang over the roof. There's a lot of things you can do to stop those pollutants getting into the water, which means it's going to be easier to work on water reuse, especially if you want to do things like flushing toilets and keep nutrients out of water, some other stuff. And you can use porous surfaces to keep water from running on. There's two ways. You can have water run off of pavement, or you can have water run onto pavement. And so you want to be careful about how you design and which way your water's moving. And each one of those has their advantage, by the way. You want to pre-treat because the things that can handle infiltration, bioretention, and long-term storage, they accomplish what no flow-based unit, similar to what we do, can do. But they are not good at trash, debris, and other things. So if you get to thinking, if you start thinking about pretreatment and the right way to apply, remember there are a lot of folks that want to take a test, like I've had a federal ETV test, and I've got another test by the Clean Water Management Trust Fund that said we got 96% of sediments out, and declare it good water quality. Well, for flow-through treatment, it is. But there's more to it than that, and I'm hoping I'm exposing a little bit of that to you, because believe it or not, the fellows in my business, in my industry, are the guys with the most data that see the most sites, see the results of pretreatment or no pretreatment on the most sites. So there's one other piece. These are post-treatment BMPs, where your water is essentially clean and you need to polish it. I use X-Tex. That's a proprietary fabric that's made, distributed by Ultratech. We use it to polish water after we have treated it. It's good at getting out metals. It's good at getting out oil. It also, if you put it in a catch basin insert, will clog with mud and vegetated debris immediately, if not sooner. Doesn't last very long. It lasts a long time at the end of a treatment train. The canister treatment devices are excellent. They're full of media. It's gravel-sized media, so it's not much at getting out really small particles. But it has a tremendous capacity, if it's kept clean, to remove dissolved pollutants and nutrients and other things from the environment that, once again, you're never going to settle out with a separator-type device. So here's my summary for this. If you aggressively design for water quantity, the volume, you can effectively accomplish a lot of the water quality, and you get a lot of water quality benefits in a lot of cases. If you have no runoff leaving the property for some storms, you're able to store it using your cistern, put it on your lawn. You get some deep level infiltration. You get some evaporation. The grass grows. That means there's no pollution leaving the property for those storms. You have a 100% pollutant removal rate at that point. Remember that detention doesn't really address water quantity. It just holds the water for an amount of time. But if you can reduce that volume going into the detention pond, that again, controlling quantity, you can make it smaller and you can make it easier to maintain. Remember that stream base flow and groundwater needs to be addressed two ways. You don't want to put a lot of pollutants into a groundwater table that's close to the surface and get those to mobilize. But you need to address keeping base flow and groundwater flow if you can. And infiltration can help if the water is clean going to that infiltration filter. Once again, each little BMP, each one of these things has their place. When you reduce the runoff volume, you help save the stream banks, and you help save flooding and downstream infrastructure issues. I've always said, yes, we're holding our water up for 24 hours, and then we're putting it in the stream. And what happens if that water, as it's progressing down the stream, and the stream's a little fuller than it would have been if there's a big storm? You know, all of us are contributing in one way or another. Everything you do to a stream to put more water in it can have an impact. Getting in the stream ahead of the storm makes some sense, unless there's a subsequent storm downstream. And so hydrology is very, like I said, it's more magic and art than it is science to me. There's definitely a science of how we predict and model flow. But what we are allowed to do under the development rules sometimes is good for the near term and not so good downstream. Using effective pretreatment not only makes reuse and infiltration practical, It makes maintenance easy and affordable. The failure of these systems, and we have systems that are tough to manage. I'm dealing with one in Tennessee right now. Because the conditions changed after the system went in, it has increased maintenance of other things. But you've got to be, you've got to understand the effectiveness of pretreatment. First of all, we do have a practical system. They're flushing toilets with it, and they're irrigating their landscape with it. It has higher maintenance than it should because, again, some changing conditions after the system was put in. All this can be addressed either with more frequent maintenance or alleviating those conditions. So pretreatment is something you definitely should think about. And, of course, doing construction, you have to remember that open land is the enemy that can erode. And there are all sorts of products that are out there, hydroseeding and all sorts of things that can help you protect open land, but try not to have too much open surface at one time. Physically controlling the water is essential. And then plan for the permanent BMPs that are going on those sites and protect those areas during the construction period. And you can use a lot of manufactured materials to lower your costs and increase the effectiveness. For example, silt fence and other things. You have to be careful, again, to try to look at controlling the erosion and not necessarily only trying to control the sediment. So there's a lot of post-construction BMPs haven't been really embraced based on cost and performance. A lot of people want to see open land, and they see man-made measures as an unnatural solution. Oh, you're not green because you're concrete and aluminum. But if manufactured devices could cut down the size of a pond by, say, 50%, reuse of water, that land can be left as a riparian buffer. It can be left as a vegetated area, perhaps with some pedestrian features, a gazebo, a picnic table, whatever. So open land, you can have more open land and have a smaller footprint by using some man-made measures as a green solution. I have to say there's the public testing that's out there on a lot of public domain solutions. They don't do very well in testing, in field testing, but there's a couple of reasons for that. First of all, they're usually poorly maintained, and there's not enough control of the design of the energy of the water in large storms as it enters and as it exits. But despite that, these solutions are flat rated as 80%. It's good. If you've got a wet pond that's this shape, you're good. As a designer, as a site designer, and as a protector of a watershed, you have to understand that's nice. The fact that I would get approved in some cities, flat rated, full treatment is nice. But you got to put some more thought into the long-term maintenance and impact on both the streams and the owners and the cost of maintenance. I have to tell you that in our industry, a lot of folks have made exaggerated claims of performance. They don't work very well. Experience could show you pretty quickly which BMPs work and which ones don't. But I will tell you that just as many, people tend to remember that, but there's just as many that are proven to be superior, both in laboratory and field testing, and some of the toughest testing in the world. I've often said that if the NJDEP regs were held up against most non-proprietary BMPs, none of them could get a permit up there. Not a single one of them would ever make it to the 80% line. A real environmentalist will seek the most effective solution for the watershed, whether it's LID, whether it's land-based, or whether it's manufactured. And the proof is in the field performance of these things. I'm not sitting here, I have to tell you, if there were bins and buckets, probably 70% of the money on water quality should be spent on land-based public domain BMPs, and maybe 30% on manufactured BMPs, which are intended to enhance those. So I'm not just sitting here saying, hey, you use one or use the other. I think I've tried to explain as thoroughly as I can that volumetric control is important and it's difficult. Manufactured units can help that, and if you're really serious about doing a low impact development, you look at that long life cycle cost, you look at the overall long-term cost of operating a system like that, and what your maintenance is going to be, and the ease of operation for your owner. And there are places for manufactured systems in LID. In fact, they probably belong in most of these systems as an adjunct to the baseline of trying to get that volumetric control in there, match pre-development conditions, and have as good a land-based system as you can. Jeff, you still with me, buddy?
Yep. Thank you very much, John. We have a couple of questions, and if anybody else has some questions, please feel free to type them. At this time, we'll open the question and answer session. However, before I jump into that, I just want to point out a few things. If you get a chance, please visit our website, and on the right-hand side of our screen, you'll see a section where you can enter your email and last name to register for our newsletter. This will keep you up to date with our webinars as they're coming out, and also any new product information and industry changes. Another thing is...
Oh, I'm sorry. Go ahead.
Another item to point out is if you go to our under engineer section of our website, you'll find about a 50-minute video, lunch and learn video on our product. I had already typed in the chat session. You can email me at jbenty@crystalstream.com for completion of certification on this webinar. And our next webinar will be on May 11th at 11 a.m. Stormwater management planning, decreasing your post-construction maintenance costs. So please be sure to take a look at those items. We'll get into the question and answers. John, you were going to add something?
Yeah, I saw the question on polyacrylamides. How does it have a negative effect or an adverse effect on a unit like ours? For those who aren't really familiar with the polyacrylamides, essentially these products flocculate suspended particles, clay particles, and they cause them to fall out. They essentially make a gel. And you talk about an extremely effective thing to use on the surface of the land, because that gel immediately gets to the surface, and they are just a wonderful thing. I learned this myself in an experiment when they came to my office to show me how we should put polyacrylamides in the front of my device, and it would make the water look really good coming out the back, which was true. It did. But in the beaker, I got into their gel at the bottom, which you don't always get to do. If you ever get a chance to go up front when someone's done this demo, go up and look at what's on the bottom of the beaker. All 100% of the clay is still in the beaker. The water's clear above it, which is the goal on the site. And our devices, if we put across, now doing construction, all bets are off. Use your polyacrylamides. They probably won't get to us. If they do, our device is going to get its gel in it. Our coconut fiber filter is going to be impacted. It's going to get clogged. Coconut fiber is of questionable use during construction period anyway. But if we want to use polyacrylamides, let's say we have a site that is putting off a lot of clay, and the water looks turbid and is turbid and needs to be treated coming out the back of a crystal stream. We certainly can't catch clay, although, as I mentioned earlier, we get a little over 7% of clay in our devices. That clay comes in attached to other things. It comes in attached to vegetative material and other larger particles, or flocculated already. But if we put it in our device, it clogs our device up. So post-construction, if we're going to use a polyacrylamide log or a dispenser of some sort, we hang it in the back pipe just out of our device, because the gel that the polyacrylamide is making is detrimental to the operation of our coconut fiber filter. I hope that answers your question, Richard.
Okay.